So welcome everyone to the ATMCS online series. So today we have two speakers, the first one being Arnur Nigmetov, and the title of his talk is Efficient Approximation of the Matching Distance for Two-Parameter Persistence.
Thank you. So I'll share my screen and then start. So can you see the slides?
Yes.
Okay, so now can I start?
Oh, yes.
Yeah. So thank you for attending this virtual talk. So it is about the matching distance, and it is joint work with my PhD advisor, Michael Kerber, and it was done when I was a PhD student at TU Graz, at Graz University of Technology. So, why? Yeah. So the plan is that I will very briefly go through some background, and I'll give the definition of a matching distance, and I will only have time to give some brief overview of the algorithm and show you some experimental results at the end. But since I only have 20 minutes, I think most of the details will have to be omitted. So just to start from some setting which is familiar, I guess, to almost everyone in the audience. In one parameter case, we can, for instance, speak about lower star filtrations when we have a finite simplicial complex, and we have a function f which assigns to each simplex a real number, its critical value, and we have a condition that if simplex sigma is a phase of simplex tau, then the critical value of sigma is at most cannot exceed the critical value of tau. And the interpretation is that if you think about this real line as time and some evolution of the simplex k, simplexes get added, then the simplex cannot appear before any of its faces. And then you can construct a filtration. So you define, so this should be 1 bar k sub t, a simplex, a set of all simplices with critical value at most t. This condition exactly guarantees that you have a simplicial complex, and you have an inclusion map, and you can apply homology functor, then you get a one-dimensional or a one-parameter persistence module that is to each real number you associate a finite dimensional vector space because we take homology with coefficients in some field, normally in Z2, and we have linear maps. And since we want to do topological data analysis, then we need some way of comparing data, because of course the motivation is that these filtrations come from some data, and after all we want to make some quantitative statements about how similar our data sets are. So we need some distance, and we can talk about distance between lower star filtrations, the distance between persistence modules, or which is most commonly done, we can talk about persistence diagrams, which essentially capture the whole relevant information about one parameter persistence modules. And in one parameter case, everything is very well studied and understood. We have a bottleneck distance. I'm not going to define it, but I'll just want to state a few properties. It is stable, so if you slightly perturb the function f, and the distance, the bottleneck distance between the corresponding persistence modules is not going to change much. And among all stable distances, this is the largest. And it is possible to compute the bottleneck distance efficiently. So it is true in the theoretical sense, and it is also true in practical sense. So you can really implement an algorithm. Well, we have an implementation in the Hera software, which computes this distance much faster. And now let's go to the real topic. So to the case of two-parameter persistence. Now we have bifiltrations. So each simplex now it's not a single critical value, but two numbers. So the function f maps into R2. And we still need to have this property. So if a simplex sigma is a phase of simplex tau, then f of sigma should be less than f of tau. What exactly does this less than mean? Well, by definition, we say that we do it coordinate-wise. So the point P is less than Q if both the x and y coordinates of P are not greater than the corresponding coordinates of the point Q. So this is a partial order on all points in plane, and you can have some points which are not comparable to each other. That is fine. And you could, in principle, depict a bifiltration like that. So you have a triangle, and on each simplex, like this vertices or these edges, you have some point attached to it. But of course, the real picture and the way to think about is as in this picture. So you have a plane, and since the vertices at critical value 0, 0, then in the whole quadrant here they are present, and this edge had the critical value 1, 1. So in the positive quadrant defined by this point, this edge is present. So this defines a bifiltration. Similar thing for the two-dimensional simplex flow. And again, we want to compare these bifiltrations. So what can we do? We could use the interleaving distance. Again, I don't have time to give the definition, but from a theoretical viewpoint, this is this is the optimal distance because it is universal. Again, it means that it is stable, and it is the the biggest among all stable distances. And it is defined not just for two-parameter persistence modules, but or bifiltrations. It is defined for n parameters, and for n equals 1, since it is universal, it must be the bottleneck distance. The bad news is that it is NP hard to approximate the interleaving distance with a factor better than 3. So we may want something maybe less discriminative. We still want something stable, but we want something computable. And the idea of the matching distance is to provide this more computable alternative by restricting bifiltrations on one-dimensional subspaces and considering all these restrictions at once. So the picture, I hope, will explain it better. You have the same bifiltration. You have this line with positive slope. This is important that the slope is positive, because then the points along this line are all comparable to each other. And then these three vertices, they are present in this quadrant, and I enter this quadrant here. So I get this point, starting from which I always have these points, and this edge I get when I hit this quadrant, and this edge I get when I hit this quadrant, and so on. So this is pretty intuitive. You get bifiltration which so by restricting a bifiltration onto a line with a positive slope, you get a monofiltration. And for monofiltrations, you can use this bottleneck distance, which we know how to compute. There's one technical issue with that. If you just say, I want to take the supremum of all bottleneck distances between all possible restrictions, then most likely you are going to get infinity. So if you have two identical bifiltrations, you will get 0. But in other cases, you will get infinity, because even if you have two simplices whose critical values are very close to each other in plane, if you make a line very close to the horizontal line, then these points where you enter the corresponding quadrants are going to be arbitrarily far apart from each other on this line. And to fix this, you need to introduce some weighting. So let's fix at least some terminology. To avoid always saying line with positive slope, I will just call such lines slices. So slice is just something like that, which goes in the positive direction in plane. And we identify these lines with with R by using the Euclidean metric. The direction is of course positive, and the choice of origin, well, actually, for purposes of definition, it doesn't really matter, because if you choose another origin, it changes nothing. But let's just say that we always translate everything in such a way that all critical values are in the positive quadrant, and then this point, the point where my slice enters the positive quadrant, is chosen as the origin. And then this point, so let's say that I have P at some critical value, and I have slice L, and this slice intersects the quadrant defined by P at some point, which we are going to call the push of the point P onto slice, well, in this case L2, in this case L1, and this push can happen in vertical direction, or it can be performed in horizontal direction. And as I said, you need to weight these pushes. So you can just say, okay, let's take this distance here and let's multiply it with a weight, which in fact depends only on the angle on the slope of this line. So basically for slices with slope less than 1, this is the sine of this angle, and for slices with which are close to with slope greater than 1, this is the cosine of this angle. The point is that this weight tends to 0 as L approaches either horizontal or vertical direction. And then you can say that to each, by associating to each simplex sigma the weighted push of its critical value in the bifiltration, the weighted push of this critical value onto a given slice L, we get a monofiltration, which, well, maybe I should refer to it as a weighted restriction of F, this weight, but I'm always going to use these things. So whenever I say restriction, I mean weighted restriction. And here comes the definition. As far as I understand, it was introduced in the paper by Biasotti and co-authors, and they didn't use the language of topological data analysis. They used the language of size theory, but this was basically, this is just the same definition rephrased in the language, which is more customary to us. You just take the supremum over all slices of a bottleneck distance between these weighted restrictions. So what are some theoretical properties? Well, the matching distance is stable, hence it provides a lower bound for the interleaving distance, and there's a theoretical result which says that you can compute it exactly in polynomial time, but the exponent in this algorithm is rather high. So it's, I don't remember, what is it, n to the 14 or n to the 16? Sorry, I think Michael is here, so sorry, I don't remember the exact exponent, but what if we just want to approximate this distance? What can we do? Why does this thing seem more computable than the interleaving distance? Well, here are some technical details, and I'm afraid I don't have much time left, so I just say that we parameterize slices, and of course this space of slices is two-dimensional, so you have two coordinates, lambda and mu, and there is a very visual argument which explains why you actually can assume that both lambda and mu range, why it is sufficient to only consider some bounded range of the values for lambda and mu. And now we can concentrate on this picture. So what do we see here? On the left, we see a slice space. In the middle, I have two bifiltrations, and on the right, I have two persistence diagrams. What would be the most naive way to compute the matching distance approximately? Let's just sample many slices in this slice space. For instance, let's just put this dense grid of points. So these are points in the space of slices. Each point here corresponds to a line with a positive slope. Now let's take this line. Oh, sorry. Let's take this line. It gives me a restriction of this bifiltration and this bifiltration. Now from these restrictions, I compute the persistence diagrams. I compute the bottleneck distance between them. This is symbolically here, and I remember this result, and then I move to the next slice and so on and so forth. So when my slice changes, these diagrams may change, the distance between them may change, and since the matching distance is defined as the supremum, I only need to keep track of the maximum. So what are the problems of this brute force approach? Well, first, you don't have any guarantees of approximation quality, and secondly, you have to sample many points in the slice space, and for each slice, you need to perform some potentially expensive computations. So even before you can get to the bottleneck distance, you need to run the persistence algorithm either on the bifiltration, or if it's a persistence module, the parameter persistence module, it's still the same algorithm, which is definitely, which in practice is almost linear in most cases, but anyway, it's not really cheap. And what is the solution to these two issues? Let's say that we have some rectangular range in the slice space with B. If we can come up with a function u of B, which provides an upper bound on the variation, which tells me how much the bottleneck distance between the restrictions changes when I walk away from the center L sub C of this rectangular region to some slice L in the slice space. If I can produce such function u of B, then the idea is that you can use the quad tree approach. So you have again the slice space. You first sample just one point. You compute the bottleneck distance here. You immediately get an upper bound using this function u. Then you subdivide. You get these four slices, you compute the bottleneck distance of the restrictions onto these slices, and you say that the candidate for the matching distance is the maximum of the 5 distances that I have computed so far. And then maybe you're lucky, maybe the distance computed here plus the upper bound on the variation of the distance on the whole of this region is less than your current candidate. Then you don't need to look into this portion of in this part of the slice space at all. It cannot improve your current estimate for the matching distance. So we can then forget about this, and other regions get subdivided, and hopefully we are able to eliminate many of them again and again. So this was actually contained in the paper of Biasotti and co-authors, and what Michael and I did, so on the one hand, there was some technical simplifications which allowed us to get simpler formulas, but what we, one step further, which we took, was that we looked at the local bounds at this function u of b, which depends not just on the dimensions of the region B, not just on how large is the difference between lambda and mu coordinates here, but really where in the slice space this box is located. And actually, if you really want the most refined upper bound u of b, then you can make it input sense specific. You can inspect each individual critical value of your point, and then you will get some upper bound which is as precise as you can get. And yeah, I think my time is running up, so I'll just have to skip all these things. So just saying that we have some theoretical estimates on how to compute the approximation of the matching distance. And it doesn't depend, so this theoretical complexity does not depend on which bound you use. So you can use what we call a global bound, a bound which works exactly the same for all regions in the slice space which have the same dimension, no matter where they are. But if you refine this, this is a constant improvement. But if you look at the experimental results, what we have here are 2 data sets where we try to reproduce the data sets used in the paper by Biasotti and co-authors. You can see that if you count the number of calls, by which I mean the number of invocations of the persistence algorithm and the bottleneck distance computation, if you just use the global bound, you may need like 11,000 calls. If you use the constant bound, which is the bound which depends on the location of the slice, on the location of its region B in the slice space, but doesn't require looking at each critical value of your filtration, then you bring this number of calls down. And if you further use the most refined bound that we have, what we call the local linear bound, we can really significantly reduce both the number of calls to this, expensive computations and also the running time here. So just to quickly sum up what we have simplified some technical issues there, like parameterization and so on. We passed from global bounds to local bounds, and so we have 2 of them, one very precise, taking longer to compute. And we experimentally confirmed that these sharper bounds are really worth having and worth implementing. We implemented this code and it is available now as part of the Hare library. It is actually, well, of course it works for two-parameter persistence modules given by relations and generators, but it also works for so in the same approach, not the code, unfortunately, but the same approach works for multi-critical bifiltrations. You just need to very slightly modify it. But what is essential here to all these details to work is, of course, that we only look at bifiltrations or on two-parameter persistence models, because all these computations of these weighted pushes and these bound derivations, they are elementary. They are really elementary geometry, but they need to be done and they rely on the specifics of the planar case, which still maybe, as far as I know, is the only case where we saw a practical application of multi-parameter persistence. So, and with that, I think my time is basically out. So thank you. I should.
Okay, so now I would ask everyone to unmute themselves so that we can thank Arnur again. Okay, so we have 2 minutes for questions. If you have a question, please remember you have to unmute yourself.
Arnur, I had a question. So I never thought of this, but these one critical filtrations arise very naturally by having a map from your simplicial complex to the plane. But is it correct to say that this is all for one critical filtrations?
What do you mean?
One critical meaning each simplex.
Yeah, it has one.
It has one appearance time, not two incompatible appearance times.
Yeah, as I said, the thing is that you really can make all this work for a multi-critical case. So you just need to in this local in the sharpest bound that we have, what we call local linear bound, because it is linear in the number of critical values. You just look at each critical value individually. You look at how much it can, how much its weighted push can deviate from the weighted push on the center, and the maximum of these things just gives you the upper bound. And you just do the same looking at all critical values in your.
I see. Fantastic. I misinterpreted multi-critical for multi-dimensional. Yeah, but I got you. That's fantastic.
Yeah. It is two-parameter, but multi-critical is fine.
Okay, we have one more question in the chat window. So what are some data sets for which the matching distance has been a useful tool?
Oh, so I'm not the paper which I saw, like the practical paper, was about I think ligands, so it has something to do with I'm not mistaken, it is drug design. So I think we use the matching distance there, and the data sets that we have here, they come from geometry processing. So you just have a 2D mesh, and you can attach certain geometric features like hit kernel signature, or some more geometric things like distances to certain planes and normals passing through the barycenter. This would give you the bifiltrations in this ED data set. I think this was used, so in the original, so like in the paper of Biasotti, they used this for shape recognition, I think. So But we didn't run any experiments on that because we were only interested in the distance computation, not actual recognition. But in principle, you could use this.